Nuclear fission and nuclear fusion are two fundamental processes that involve changes in atomic nuclei, but they operate in opposite ways and under different conditions, each with its own unique set of implications for energy production. Nuclear fission is the process by which a large, unstable nucleus, typically of a heavy element like uranium-235 or plutonium-239, splits into two smaller nuclei, along with the release of a significant amount of energy. This process occurs because the nucleus of such an atom is held together by strong nuclear forces but is also under the stress of repulsive forces between the positively charged protons. When a neutron collides with this large nucleus, it can cause the nucleus to become even more unstable, leading it to split into two smaller nuclei, known as fission fragments. In addition to these fragments, the fission process releases several neutrons and a tremendous amount of energy in the form of kinetic energy of the fragments and gamma radiation. These released neutrons can then initiate further fission reactions in nearby nuclei, creating a chain reaction. This chain reaction is the principle behind nuclear reactors, where the energy released is harnessed to produce electricity. However, the same process, when uncontrolled, is what drives the explosive power of nuclear weapons. The energy release in fission is due to the fact that the combined mass of the fission products and neutrons is slightly less than the original mass of the nucleus and the neutron that initiated the process. This difference in mass is converted into energy according to Einstein's equation, E equals mc², where even a small loss in mass results in a large release of energy. Nuclear fusion, on the other hand, is the process in which two small nuclei, typically isotopes of hydrogen such as deuterium and tritium, combine to form a single, larger nucleus. Fusion requires extremely high temperatures and pressures to overcome the electrostatic repulsion between the positively charged nuclei. At such high temperatures, the kinetic energy of the nuclei is sufficient to allow them to come close enough for the strong nuclear force to take over, binding them together into a larger nucleus, usually helium. This process releases a massive amount of energy, even more than fission, because the mass of the resulting nucleus is slightly less than the total mass of the original nuclei, with the lost mass again being converted into energy. Fusion is the process that powers the Sun and other stars, where the immense gravitational pressure and high temperatures allow fusion to occur naturally. On Earth, scientists have been working for decades to develop controlled nuclear fusion as a source of energy because it has the potential to provide nearly limitless energy with minimal environmental impact, as it produces little to no long-lived radioactive waste. However, achieving the conditions necessary for sustained fusion reactions has proven extremely challenging, and while progress is being made, practical fusion energy remains a goal for the future. In summary, nuclear fission involves the splitting of a large, unstable nucleus into smaller fragments, releasing energy and neutrons that can sustain a chain reaction, while nuclear fusion involves the merging of small nuclei under extreme conditions to form a larger nucleus, releasing even more energy. Both processes involve changes in the mass of the nuclei, which is converted into energy, but they operate under very different conditions and with distinct applications.